Today we'll be continuing with Chapter 2, looking at Section 2.6 on transformations of functions. I find that most of the time students really enjoy this section and do well with it and have a lot of experience with it, so hopefully you'll find that to be the case today. Okay, to get started, there are a couple parent graphs that I really want to remind you of. The better you understand and remember these graphs from section, I think it was 2.2, the better you're going to do in this section. So when we're talking about a line, that's going to be of this form, y equals mx plus b. Just remember that your parabola, your x squared, looks something like this. Your reciprocal function looks like this. Your cubic function like this. Absolute value, and your square root. So just keep those in mind. It'll make the transformations we're going to be looking at a lot easier. So the first transformation that I want to talk about is vertical shifting. So anytime we take our function and we add or subtract something to it, it's going to move it vertically. If we add to it, it's going to shift it up that many units, and if we subtract, it's going to shift it down that many units. So whatever's added or subtracted out the end of it is going to be a vertical shift. Okay, throughout this section today, I want to hop over to Desmos and do a couple of demonstrations. You may or may not be familiar with that. It's a free service. If you're interested in playing around with it a little bit, then I would encourage you to do that. So I'm over here at desmos.com/calculator, and again, that's a free service you can use. So what I want to do is start out with one of our parent graphs, which is x squared. So x squared is simply this parabola that you see here. So I want to graph a couple vertical translations. So if I go up, if I do +4, okay, then you can see here it took this red graph and actually just slid the whole graph up by 4. If I look at another one, if I do x squared and I do -2, then it's going to again take this parent graph, which is just that standard graph that starts at the origin, and it's going to slide it down 2 units. So we can do all kinds of different things with this as we go on through this section today. We could shift it down 8 units, and you can see that the whole graph, it looks bigger, but it's not actually bigger. It's just as being slid down. You're seeing the wider part of the graph instead of the more narrow part of the graph here. Okay, so when we start looking at problems like this, part of what I want you to be able to do is to identify the parent graph and then to tell me verbally or like in words what type of translation is happening, and then to be able to sketch your graph. So on this one, our parent graph is, and I'm just going to put a P, our parent graph is simply x squared. So our x squared graph is symmetric here about the y-axis. So if we go, I'm really just going to get a few points here. Okay. Right. So we start out with our parent graph, and we want to, this indicates that we want to go up 3 units, and that's what I want you to be able to tell me is the direction that it's going to move. So every point is going to slide up by 3 units, and then we're going to sketch it in. And with the use of the computers and the calculator, I'm not too concerned about you're actually, graphing this specifically, but you should be able to indicate that it's shifted up by 3 units. Here, this one again, the parent graph is simply x squared, and this one indicates it's shifted down by 2 units. So we start with the same standard graph, except we're going to move it down 2 units. So it's going to look something like this, where we've taken and shifted the whole graph down by 2 units. Okay, if you look at this more professionally done graph, you can see again the blue is going to be the parent graph, the red is the shift up 3 units, and the purple is the shift down 2 units. Okay, moving on to horizontal shifts. Horizontal shifts occur within the function, and they're going to move either right or left. I will say it's a little bit different than you think. If this is x minus some number, like for instance, an x minus 3, and it's inside the parenthesis or inside a square root or inside an absolute value, then it's going to move opposite. So as you can see, this one is has a negative here, but it's actually moving to the right that many units. Over here, if you have a positive, that means that we're going to actually move back to the left. So when you're inside of something, it's kind of the opposite of whatever that sign is. So again, I want to show you what these translations are looking like. So I'm going to start again with the parabola. And this time we want to look at horizontal translation. So I'm going to go inside of my parenthesis. And okay, so looking at this, what you can see is this has a minus sign, but if you notice, this was shifted to the right 6 units with that. So anytime we have a negative, it's going to send us to the right that many units. If I have a plus, then you can see that it got shifted to the left that many units. If I want to change all this, I'm going to get rid of these parent graphs here and work with the square root graph. So let's do the square root of x. That's going to be my parent graph. And then if I do the square root of, let's say, x minus 5, then you can see that my parent graph got shifted 5 units to the right. And if I do the same thing and do the square root of, this time, let's do x plus 2, then you can see that that got shifted 2 units to the left. We could do the same thing with absolute values. If we have, if we have the absolute value of x, then here's our v graph. And if we do some kind of translation to it, for instance, x plus 3, you can see that that moved it to the left 3 units. And again, if I do maybe x minus 4, that's going to move it to the right 4 units. So whatever happens inside the parentheses is going to shift it left or right, depending on if it's a positive or a negative. Okay, so this one's another one working with x squared. If we have a plus 4 here, because it's inside the parenthesis, that's going to send it to the left 4 units. So where it would have normally started here at the origin, it's going to send it left 4 units. So our graph is going to be sitting over here like this. Okay, here we've got a minus inside, so we're going to send this one to the right 2 units. So instead of again sitting at the origin, it's going to sit right 2 units. And we'll sketch that in roughly, and that's what our graph is going to look like. Okay, and again, this is a much more professionally done graph to kind of see what these should look like. Okay, on this one's a little bit more complicated. It's combining a couple things together. If you see here, we've got the square root, so our parent graph is actually just the square root of x. So I'm going to go in and graph this. Our graph is going to look something like this. If you remember the general shape of the parent graph for the square root of x. Since this is inside the radical, this is actually going to move it to the right 3 units. And then since this is outside, it's going to move it up 4 units. So if I go up 4 units and I go right 3 units, this point here is being relocated to this point here. And so I'm then going to have a graph that looks something like this. Okay, here's another one. If we want to identify the parent graph, we've got this square term here. So my parent graph is x squared. This part is inside the parentheses, so I'm going to move this left 3 units. This part is outside, so I'm going to go down 5 units. So I would have normally started at the origin for this point, for this graph x squared. This time I'm going to go left 3 and down 5 and start my graph at that location. Okay, so that's what my graph would look like. Okay, reflecting graphs, we do a lot of reflections, especially reflections in the x-axis. Anytime you see a negative in front of the function itself, that's going to be a reflection in the x-axis. If you see a negative inside the function, then that's going to be a reflection in the y-axis. So basically, if I took this graph reflected in the x-axis, it's going to be like I'm folding my paper here on the x-axis and folding it on top of this down here. So my graph's going to move from here being down here. If I'm going to do a reflection in the y-axis, same thing. It's going to get reflected from here over to here. So on this one, I want to start out again with the x squared. That's just a good graph to look at. So if I put a negative in front of that, then putting a negative in front of the function is a reflection in the x-axis. So you can see what happened here. If I look at some other graphs, if I look at my square root graph, I'll do the parent graph there. And then if I do another square root, but this time put the negative, actually, I'm going to put the negative in front of it. Okay, then you can see how it took this red graph and reflected it down here. Okay, so all of those are reflections in the x-axis when you stick a negative out in front of it. If I change it and I want to do a reflection in the y-axis, I'm actually going to take off some of these here. So I'm going to look at this square root graph. If I want to do a reflection in the y-axis, then I'm going to have a negative inside of the function, and you can see that it went from being over here to being over here. Another parent graph we haven't talked a whole lot about is the x cubed function. So you see that one in purple. If I wanted to do a reflection in the y-axis, then I would put the negative inside of this, and you can see that it's going to be reflected in the y-axis. One thing I want you to notice on this one, which is actually true on different graphs, is that if I were to put it in front of the whole function and do a reflection in the x-axis, I actually get the same graph. So sometimes your x-axis reflection and your y-axis reflection are going to be the same thing. So we just looked at these. I do want you to be specific about this. I don't want you to say flipped or turned upside down or anything like that. I want you to say this is reflected in the x-axis, because here we have a negative out in front. So where our normal parabola would have opened like this, we're going to have this one that's going to open upside down. Okay, so it's going to be reflected in the x-axis. Over here we've got the negative inside, so this is one that we did on Desmos. So our normal graph, our parent graph would have looked like that. This one's going to look like this, reflecting it in the y-axis. Okay, so this one would be a reflection in the y-axis. Okay, so again, you can see this a little bit clearer with these graphs. Okay, vertical stretches and shrinks. Anytime we have a function and we multiply it by some kind of factor, if the factor is greater than 1, then we're going to have a stretch. If the factor is between 0 and 1, we're going to have a shrink. One reason we don't look at negatives is because we just looked at what a negative does. A negative will reflect it in the x-axis. So here, I always think of it like if you had like push pins and you pinned this here, here, and here, if it was like a rubber band and you stretched it, it's not going to change our intercepts, but it is going to stretch the graph and make it thinner, so to speak. So here it's going to be stretched thinner if you have C being greater than 1. Here it's going to be closer down to the x-axis, not stretched quite as much if C is between 0 and 1. Okay, so here again, we're starting with x squared. So what I would like to do is to look at some different vertical stretches. So if I put a 3 in front of the x squared, you can see it gets thinner. If I were to put a 10 in front of the x squared function, it gets even thinner than that. But if I were to put a number between 0 and 1, then I'm going to get, let's say 0.2x squared. Then you can see it gets fatter, so to speak. It gets pushed closer to the x-axis. It's not stretched as thin. If I were to put an even smaller number, let's say 0.01x squared, then this parabola gets really flattened out here. It does have some curvature to it, but just not a lot. So you can kind of see the effect on this. And this is true for our other parent graphs as well. if I were to look at, let's say, the absolute value of x, and if I put a number in front of that, like a 7, then it's just going to stretch it more. You can see in the green graph there. And if I were to put like 0.25 in front of it, then you can see that it kind of flattens it out. So hopefully you're seeing what these vertical stretches can do. So on this one, we're again working with a parent graph of x squared, and we want to identify each transformation in words. So here I have a number multiplied to my parent graph, my parent equation, and it's greater than 1, which means this is going to be a vertical stretch. It's going to start at the same location, except it's going to be stretched much thinner. It's going to look something like this. And as far as the specific points, I'm okay with you getting those off your calculator, but I do want you to recognize what's happening without having to go to your calculator every single time to describe it. Here we've got 1/3. 1/3 is less than 1, so this is going to be a vertical shrink. So it's, instead of being like looking like this for the standard parent graph, it's going to be much flatter looking down, something like this. And again, you can see these more exact here. Okay, on this one, I want you to identify the parent graph, describe in words the transformation, and then sketch the graph. So on this one, our parent graph is going to be the x squared, because that's the basic graph we're working with. We've got several things going on. The first thing I'm going to actually do is rewrite this. I'm going to put -2 times x minus 3 squared plus 1. So hopefully you can take a minute to verify that you agree that this is equivalent to this. All I'm doing is moving the 1 to the back side of it here. So when I look at this, I see a few things. I see here this negative is going to be a reflection in the x-axis. Okay, the 2 here is going to be a vertical stretch. The -3 is going to move it to the right 3 units, and then the +1 is going to move it up 1 unit. So as far as sketching this, we know our basic graph looks something, sorry, not the square root graph. It looks something like this. So we're going to need to reflect it. We're going to need to stretch it. So it's going to stretch a little bit thinner. And then we're going to need to move it to the right 3 and up 1. So it's going to look something like this. And it's not a V. I'm just having some trouble getting this drawn like I would exactly like for it to be. But that's what we would expect for our graph. Okay, one thing I would recommend is take care of your reflections and your stretches before you take care of your shifts, either the shift to the left and right or the shift up and down. Okay, horizontal stretches and shrinks. We don't see these quite as often. I do want to take just a couple minutes to talk about them. So they're very much opposite of what a vertical stretch is. So if we've got C is greater than 1 here, then what that's going to do is actually going to shrink the graph. So that's a change there. Shrink the graph horizontally by a factor of 1 over C. If it's between 0 and 1, it's going to stretch the graph horizontally by a factor of 1 over C. So I'm going to kind of go over to Desmos and show you what I'm talking about. Here, like you can kind of see it a little bit here. If C is greater than 1, then we see that shrinking around the y-axis here. And if C is between 0 and 1, then it's actually stretched out as it is on this graph here. Okay, so let's start back with our standard parent graph for our parabola x squared. This time what I'm going to do is I'm going to put the factor that it's changing by inside the parenthesis, which means it's going to be either a vertical, excuse me, a horizontal stretch or shrink. So if I put in a 4, okay, so if I put in the 4 inside of here, what you can see is it looks like, and it is a vertical stretch the way because this is going to end up being equivalent to 16x squared. But you can see also that what it did is it shrunk it near the y-axis. So it shrunk in from here to here, and it shrunk in from here to here. So when you're talking about horizontal shrinks and stretches, if you have a number here that's more than 1, you're going to see a horizontal shrink in toward that y-axis. Okay, if I look at another one, let's do 1/4. Okay, so you can see that now this one was actually between 0 and 1 that I put inside there, and it actually took and pushed it further out than what it was. So this was our standard, it pushed it further out, so it stretched it along, stretched it horizontally is what that had the effect of doing. Okay, let's look at the absolute value graph for just a minute here, and then we'll move on. Okay, so we've got our basic parent graph, and let's look at the absolute value of 4x. So you can see that inside there, it actually shrunk it horizontally. And then if I look at 1/4 x inside, you can see that it stretches it horizontally. And some of these horizontal effects are very similar to a vertical effect as well. So keep that part in mind. So this problem here is one that deals with horizontal stretches and shrinks. Most of the time we work with parent graphs that are those that we have become familiar with. Sometimes our parent graph is defined as a new graph, and so that's what's happened here. This top graph is going to be acting like our parent graph, and so throughout this is the graph that we're going to denote as f of x, and we're going to do the horizontal stretches and shrinks to this particular graph. So if you look at this first transformation that we have here, we've got a 2 that's inside of this. So what that's going to do, because this is greater than 1, this is going to be a horizontal shrink. So it's going to take and it's going to move each one of these points in, and the factor is 1/c. So this is the c. So the factor is going to be by 1/2. So what was originally at 1 is going to now be at 1/2. So this is kind of enlarged a little bit, but you can see that this slides into to be here at 1/2. So every point is going to be multiplied by 1/2, so to speak. So this one would have been at 2, now it's at 1. So everything just gets kind of like an accordion that's getting condensed and smashed together here at the vertical axis, at the y-axis. Okay, if we look at this one here, this is our C, so we're going to have a horizontal stretch because the C is between 0 and 1, and the factor is going to be 1/c, so 1/1/2. So keep, change, flip, and I get a factor of 2. So every point is going to be multiplied by 2. So what was originally at 1 is now going to be out here at 2. So it goes and it gets moved, it gets stretched out to 2 for that. Okay, so the last thing I want to look at in today's lecture is even and odd functions. This has a lot to do with symmetry as well. So basically what we're going to do is we're going to evaluate each function at -x and simplify it and see what type, whether it's an even, odd, or neither for our functions. So an even function is symmetric with respect to the y-axis. So in testing for an even function, basically we're testing for y-axis symmetry. If we're testing for an odd function, we're testing for symmetry about the origin. So always remember your O's go together, odd and origin. That's an easy way to remember that those two work together. Okay, so I've made this chart for you to help you decide which one it is. So the first thing you want to do is evaluate f of -x. So plug -x into your function, simplify it. When you simplify it, if it's equal to the original, then it's an even function and it would have y-axis symmetry. Okay, if you simplify it and it's the negative of the original, which means that it has completely opposite signs of the original function, then it's going to be odd and it's going to have symmetry about the origin. And then if you simplify it and the signs are mixed, okay, meaning some match with the original and some are opposite the original, then that's going to be a neither case. And so, so if you don't get either the original or the negative of the original, then it's going to be neither. Okay, so here are a couple examples for us to look at. The first one, we're going to plug in negative x and evaluate it. So we'll have negative x to the fifth plus negative x. So when I simplify this, a negative to an odd power, the negative will come out in front. Okay, so when I go to compare this to the original, I can see that each sign is the opposite. So this one was originally positive, now it's negative. This one was originally positive, now it's negative. So that's the negative of the original. And when that happens, it's an odd function. Here, if I plug in negative x and simplify, I'm going to have 1 minus a negative to an even power is going to become positive, but I still had this negative out in front here. So when I compare this to the original, it's the same. So if it equals the original, then that's an even function. Here, I'm going to evaluate it at negative x. So this will be negative 2x minus, this is going to be x squared. Okay, so I'm going to compare this to this. So here, this was a positive, and now it's moved to a minus. But here it's a minus, and it stayed a minus. So it's not the same, and it's also not the opposite signs. So this one's going to be a neither case. Okay, and so these are just the graphs of the ones that we're looking at here. The first one, we said, if we look back, you can see that it was odd, and the graph of this shows that it's symmetric about the origin. If I took this point and spun it 180 degrees, then you could see you'd be down here and so forth. This one was the second one we did. It was symmetric about the y-axis, and this was an even function. And then this one you can see does not have any kind of symmetry, and it would have been neither. Okay, that takes us to the end of today's lesson.